they're not very easily explainable or interpretable. And you can't, there's beginning to be work in interpretability about how to analyze these, but really it's like a soup of math, and it's like at a very, very large scale with billions and trillions of parameters. So people are just starting to do work that attempts to interpret them. But in addition to being black boxes, they also struggle to generalize to unseen domains and tasks. Recently, the way to try to attack this is by internet scale pre-training and scaling your models. But people have been doing that for several years now, and several benchmarks still remain unsolved. So it's probably important to consider other paradigms as well, besides end-to-end neural networks. And so in 2016, there was a different paradigm proposed by Jacob Andreas and others. And they said that, and this is the neural module networks. So this is a modular architecture to solve vision language tasks. And they said that language is compositional. And what that means is we should actually be using a method that decomposes the tasks into components, and then solving those components independently, and then finally bringing them all together. So in this method, what they do is they decompose the question or the query into these neural modules. The types of modules are attend, classify, reattend, combine, and measure. We'll show some examples soon. And I'll go through some more examples. I'm not sure how intuitive this figure looks, but the dream for them was to learn reusable modules that do these primitive skills that generalize to unseen questions and layouts. So as long as you have a good enough parser, you can come up with a layout of modules. And as long as you've learned each of those modules really well, then hopefully you can answer any question. And you'll notice that this is also no longer a black box. You can actually see what are the decisions being made inside this modular network, and so that's a good step in the right direction that end-to-end neural networks don't handle. So just a simple example from the last slide, you might want to parse where is the dog, and in order to do that, you might have first, you select the attend dog module. That's a specific module. So you might also see other modules to choose from, like attend cat or attend bookshelf, things like this. But it's of the type attention, and this is a visual attention, not like in the language models that we see these days. So that means first you might apply this filter to understand where is the what in the image is relevant to finding the dog. And then you might take that input as well as the image, and you pass it through the next layer, which is a classification layer that says classify where. So classify where, and then you take the inputs of attend dog, and that together forms the module where the neural module layout. Where is the dog? And this classification basically classifies this as the couch. Just a couple more examples. On the left hand, we have what color is the vase. So first you attend to vase, then you classify the color of it. And there are some other examples here as well. Maybe the one on the very right is there a red shape above a circle? So you can see this is a very compositional task in nature. First, if you start from the very bottom, you have to attend to circle. Then after you attend to circle, you can then reattend to above circle. And you can combine that with the attention for red. And then you can measure is, which is another classification layer. And so altogether that forms, is there a red shape above a circle? And the hope really is that if you train this on enough examples, you should learn a lot of reusable components for things like measure is or attend circle. And then when you ask a new question that's unseen, all you have to do is parse it. And finally, if you've learned all the submodules well, you can bring it together and it'll solve that task as well. So then it was actually state of the art on the VQA task back in 2016. So that's actually pretty great. But there are a lot of details about the implementation and how future attempts at this work handled things. So in this work, they tried to learn the decomposition, the perception, and the modules jointly. They also used a hand-tuned parser for parsing the natural language questions. And later attempts also started to use optimization algorithms with reinforcement learning from scratch. So all of these things are actually really hard to train. And they found that this approach didn't really generalize well to new domains like they'd hoped. So there was rather little progress in modular vision in the years after. But in 2023, modular vision is back. There are a few approaches that were pretty viral that did modular vision, and people were really excited because they were the first to outperform end-to-end models on zero-shot vision language tasks. Specifically, there are these three methods: VisProg, ViperGPT, and CodeVQA. And I think these were the prominent ones. And they're all kind of concurrent works. Each of these works takes a long time to work on, so there's definitely a lot of overlap. And we'll just enjoy this slide. You don't have to look at all the examples, but we'll talk about them shortly. Generally, all of them take an approach that looks like this. This is like the schematic of all of those approaches. First, you have this question or a query, and you give it to a large language model to decompose that into a program. So like this, that's this part right here, the decomposition of the question, right? Once you have the program, then you can use the interpreter to execute that program using the image, because you're doing manipulations on the image, and using some set of modules. So those are maybe neural network modules, maybe they're symbolic modules. We can talk about that. And whenever the interpreter does this calculation, it comes up with a prediction, and that's your answer. In this work, we specifically analyze ViperGPT. It's kind of an arbitrary decision. All of them are methods that we could be looking at, but each of these is very complex, so we focus on ViperGPT for this work. And this is also one of the first works. Our work is one of the first works to start analyzing these approaches. So I think it'll be really exciting to see more efforts in this area as well. In ViperGPT, you might have a question: how many muffins can each kid have for it to be fair? And for now, I need you to imagine that there's an associated picture with that. But what they do is they take that query and they decompose that. And so they use a large language model to decompose that into this generated Python code. This Python code says, let's execute the image, and then there's the execution step. So here's actually the original image for that question. And again, that question was, how many muffins can each kid have for it to be fair, right? So basically, you want to see how many muffins there are, and you want to divide by 2 and make sure it's fair. And what the Python code does is it takes in the image. It analyzes the image using the find function to find the muffins. So you can see it in the diagram on the very top right. When you do image patch.find muffin, you get back all the bounding boxes that correspond to muffins in this image, and there are actually 8 of them. You can also do find kid, that's the green box, and you can find the 2 kids. And now you have these like symbols inside this network, and you can then count how many muffins there are using, this is a Python length operator. So there are 8 muffins, there are 2 kids, and you can do a division that says 8 divided by 2 is 4. And so if each of the kids gets 4 muffins, that's what's fair. So, I mean, this is, I think, really amazing. You can see how big of a step forward this is from the previous work we talked about, neural module networks. And this really has all the bells and whistles of deep learning today. I want to point out that this image patch.find function is powered by neural networks. So that's GLIP, which is like pre-trained region-based image language model. And they also have symbolic operations with the Python interpreter, like counting this length and doing this division. And so we saw that schematic of these modular approaches in the previous slide, but this is the schematic that's specific for ViperGPT, where specifically we take this question, we have a prompt associated with it, and we give it to the OpenAI's Codex model. This was one of the previous GPT models that was trained specifically on generating code, and you can use that to generate this code. Then you execute that using the Python interpreter, along with the set of modules that have been predefined for these tasks. Like blip2 is what they're using for visual questions. They can use LLMs. They can use the symbolic algorithms, etc. Just want to show you a couple more examples. For example, here we have this picture of the two pizzas in the top right corner. And the query is pizza front. So you want to get the pizza, the image of the pizza that's in the front. And so how they do that is in green, they first do image patch.find pizza, and you can find the two pizzas in the image. Then you can compute the depth. So you see that the bottom pizza has a depth value of 0.3. I think that might be in meters. And the further one is 0.7. So clearly the pizza with the higher value is closer. You can sort them according to their depth. And then finally, once you sort it, you can take the first element of that list, that is the closest pizza, and you can return that one. And it ended up being the pizza that is in the front. So it was correct. And then there's a bit of a longer one. What would the founder of the brand of the car on the left say to the founder of the brand of the car on the right? So you can see that there's a left car and a right car. I think the left car is a Lamborghini and the right car is a Ferrari. So the way they do that is they find the cars, then they sort them based on the horizontal center of each detection. And then they have to figure out, so now we know we see which boxes correspond to the left and the right car. Then you can ask a visual question. What is the brand of this car? So given the box that corresponds to the car, you can ask a visual question about that using the VQA module. And that one's blip2 as well. And the brand of that car on the left is a Lamborghini. The brand of the car on the right is a Ferrari. Then you can ask GPT, who is the founder of, and then you insert the brand of the car on the left. So who is the founder of Lamborghini? And that's Ferruccio Lamborghini. Likewise, who is the founder of the right car brand? That's Enzo Ferrari. So what would left car, so Ferruccio Lamborghini say to Enzo Ferrari, and then you put that, and then it's using the GPT module, and that'll just respond with this quote that Ferruccio Lamborghini might say, "It's been an honor to be a rival of yours for so many years, ... So this is actually a really complex example, and you can see it's handling this decomposition really well. ViperGPT can also process videos, but in our work, we're just looking at the image component for now. Maybe future works can also analyze the video processing component. And so let's break down a little more about how it works. ViperGPT has an image patch API. So this is specifically a prompt I'm showing you. So this is like what is given to the language model to help it decompose the questions into code. So these are functions you can call. For example, we talked about the find function already. If you have an image, you can ask it to find the toys, in which case you'll get detections for where each of the toys are. You can do verify property. So, you know, if you say scarf red, that means is the scarf in the picture red? You can do best text matching. Is the image more blue or is it more red? Best image matching. Which of these images like matches well with both bread and cake? That doesn't necessarily mean the cake is red, but maybe if there's something really red in the image and also that there's a cake, that'll work. You can compute the depth. You can ask visual questions, and then you can also ask language questions. So what that actually translates to translates to is about 300 lines of this prompt, and it's written in Python code. But really, this is what you feed the language model in order to help it understand what functions it can call and how it can call them. And you can see there are green comments in this API. And we'll go through a specific example. You don't have to read all of this slide. But if you give this prompt to the decomposition model, it should be able to generate a program for you. So specifically, this prompt has a class called image patch, and we'll just look at one little snippet of that class. That's the find operation. And so this is the API for find that says, if you're calling find, this returns a list of image patch objects matching the object name. Otherwise, it returns an empty list. And it actually shows an example here of how you might do that. So if the query, if you're looking at the very bottom at line 87, if the query is return the children, then the way you do that is you create a function that says find the children in the image patch, and then you should return that. And so some of if you look back at that API, there's a lot more in here, and some of these have more detailed examples with more compositional structures using multiple functions. And under the hood, how this actually works is, remember, this is actually just what I've shown you is just the prompt for the language model. This isn't actually the implementation of this function. There is there's an actual script that corresponds with these functions, and that is doing more complex things, like it starts to call these neural networks. For example, there's GLIP for object detection. There's something for depth estimation, text-image similarity. There's BLIP2, which we mentioned before, which is for answering visual questions. And there's GPT for a text completion. You also have these symbolic operations that you're able to use, loops and sorting and arithmetic and if-else and more things you can import. And so altogether, how that works is you have this prompt, and you give the prompt that says, how do you decompose a question into code, to codex? You also give it the question of your interest. And then that together generates this code, which is like that execute, it's called execute command, right? Like in this example. And so now you have some Python code that you can actually run with the Python interpreter, as long as you have an implementation for that image patch API. And they do have an implementation for it, and they use all these neural modules, BLIP2 and the like, as well as some symbolic algorithms. And they provide the image as well to this function. And so then they can use the actual Python interpreter to actually execute this code and call these submodules and come up with a prediction. And so this is actually a pretty complicated framework, but you can see a lot of convergence from some trends in NLP here. We're prompting language models, we're generating code, and there's this other phenomenon, tool use, that also sees some light in NLP. And so we're bringing all of that together in this one big framework. And so what their takeaway is that ViperGPT outperforms state-of-the-art zero-shot neural networks. Like I said, it's the first time a modular approach has done this. And I'll say it's for not just ViperGPT, but the other two methods I mentioned earlier, VizProg and Code VQA. They all do this kind of thing. But specifically, ViperGPT compared to a few benchmarks, some for referring expressions on the left, which is like a vision language task about identifying what parts of an image correspond with the query, and then some for the VQA style tasks on the right. So you can see that in blue, you have the prior state-of-the-art neural networks, Reclip on the left and BLIP2 on the right. And then you can see that ViperGPT actually outperforms these maybe significantly, right? On this RefCoco example, it's like plus 10 points, maybe more modestly on others, just a few points, plus 4 points. But this is a really exciting result. So we wanted to ask some research questions. We were really inspired by this work, and it's really exciting, and we wanted to understand more about it. So we asked a few questions like, do they generalize to tasks they haven't been engineered for? These methods are really complex, so where specifically does their performance come from? And is code the necessary mechanism for decomposition? And so we have a methodology, which is we focus on the visual question answering task. And it doesn't really matter what task you pick. For simplicity, we picked that one. You can test on multiple tasks, but we picked 5 modern benchmarks for VQA. And so VQA V2 is the first one. That's less modern, it's more solved. But that ranges to harder benchmarks, GQA, OK VQA, AOK VQA, and Science QA. And they all, I'll show you some examples in the next slides, but they all vary in the amount of perception, the compositionality, the knowledge, the reasoning they need. So some of these benchmarks are actually pretty challenging. And we evaluate the models. I'll tell you what models we evaluate, but we evaluate them on these benchmarks using 2 metrics. One is the original metric that corresponds with each of these data sets. But we actually found that those original metrics are based on lexical similarity. So for example, if the ground truth answer for one of these questions is dog, then dog, the only acceptable answer would be specifically dog or some variant of that, but it wouldn't be golden retriever. So I think the language models that are now being used and employed for this kind of task are more likely to produce more complicated answers. And so these lexical metrics aren't really good enough to handle those correctly. And so we found that the instruct GPT eval, this is an LLM-based evaluation strategy by Kamalu et al. That's actually a more robust metric for computing this kind of evaluation. And we had to rigorously test this. I don't think it's appropriate to use LLM-based strategies in all cases, but we made sure that it only brought improvement to the metric in our case. And I can show you more if anybody has questions about that. So let's just look at a few examples from these benchmarks. On the left, there's that VQA V2. This is a more classic benchmark, maybe from 2014 or so, 2015. And so you're asking questions like, has the food this woman is preparing been fried? And so in order to answer that, you have to first find the food the woman is preparing and then ask whether it's fried. You know, in this case, it's a salad, it's not been fried. You can look at examples all the way to the right. In AOK VQA, the company that has produced the device in her hand is from what country? So what is the device in her hand? Actually, if we look, we can see that's a Wii controller. A Wii is produced by Nintendo, and Nintendo is from Japan. And below, on the bottom, there's Science QA, which asks some kind of difficult reasoning questions. This actually looks pretty easy. What property do these 3 objects have in common? They might be bouncy, hard, or soft. But actually, like, I think this diagram is just out of the visual distribution of the pre-training for these models. So that itself might provide a little bit of a challenge. And also, some of the other questions in this data set are much more challenging. They rely on better knowledge of physics and things like that. So we make one observation, and it's that when Viper GPT, they evaluate their benchmarks on each of these tasks, they actually use a prompt that's specifically curated for that task. So they don't give the full API, which I showed you a few slides back with the 300 lines of code for every arbitrary task. They specifically select a subset of that API, and that means they're also selecting a subset of the modules that are available for them to compute for each reported benchmark. For example, for computing the GQA score, they only use the simple query function and the best text match function. So that's only 2 out of the 12 available functions. Do you have a question? No? Okay. And so, yeah, so, you know, that's interesting because that means they specifically had to do some engineering work in order to figure out which are the best modules specific for that task. And if you think back about the objective of generalization that we talked about earlier, that means ideally in a system, you shouldn't have to curate the system for every new style of questions it might see. the goal is that our system will generalize no matter what. So we asked, how will the performance change when you give it the full API of 12 functions? And so we found that while we saw the original results on the left of the task-specific prompting that was reported by ViperGPT, we redid this analysis using a task-agnostic ViperGPT with all 12 modules, regardless of the task. And then you can see that specifically on the two benchmarks that we both compared, GQA and OKVQA, while they had showed an increase in performance of ViperGPT compared to the state-of-the-art BLIP2, the end-to-end state-of-the-art, we actually showed that ViperGPT had a more marginal gain on GQA. That's a smaller gap on the right-hand side. Notice that my axes are scaled. You'll have to look at the paper for the real numbers. The gap in the gains in GQA are smaller, and the gains in OKVQA are actually losses. So while there were gains on the left side with the task-specific prompting, we found the performance drop with the task-agnostic prompting. And we see that trend continuing for AOKVQA as well. We also ask if it can generalize to new tasks that's outside of the distribution of ViperGPT's engineering. So specifically, it was, in a way, the prompt was written with GQA and OKVQA in mind. Those are the tasks that it was evaluated on in the original paper, but it wasn't evaluated on an AOKVQA and Science QA. So we wanted to see how the task-agnostic ViperGPT would do in those data sets. And so in the AOK direct answer setting and the Science QA multiple choice setting, we can see it continuing to drop a little bit compared to BLIP2. But we can see that in the AOK VQA multiple choice setting, it did present a significant boost. Now, we also looked at the failure rates of this method when you look at tasks it was engineered for, and then also new tasks. And you can see that for the tasks it was engineered for, VQA, GQA, and OKVQA, there's almost no exception, 98 or 99% more of the time. AOKVQA is of a similar distribution in the direct answer setting. So there's a few more errors, 4%, but not too many more. But then the multiple choice settings of AOKVQA and also of Science QA, which is very different, that has almost a 10 to 20% error rate. And so we count this in the Python errors, whether there was a parsing error, that's an error that points to a failed decomposition by the language model, or a runtime error. That's a failure of probably, like, that it can also be a failure of the decomposition, but also of whether the modules executed in order worked consistently. And finally, and so basically that means that when you generalize to new tasks, you are more likely to see errors. Finally, we also make an observation that BLIP2 is actually a component in ViperGPT. So you're comparing the state-of-the-art BLIP2 network against a system that contains BLIP2 inside it. And if you look at the previous slide, we saw like performance drops actually compared to BLIP2 in some cases, or some just small gains. And so you can refer back to our paper for the full table. I couldn't figure out a way to make it digestible here, but the conclusion is that we did this analysis where we removed BLIP2 from ViperGPT, or we removed all the modules except for BLIP2. And we found that ViperGPT does retain most of its performance, at least within like 80% of the performance, if you do either of these significant modifications. So that means you don't really need that much more than BLIP2. But if you were to, which is like the critical module, if it's the VQA module, that is a module that the VQA tasks can rely heavily on. So if you remove that, that's kind of a seemingly critical module, but you retain the other modules. So that'll be things like the object detection module and the counting module and things like that. You can actually still keep some of the performance. So I thought that was really surprising. And so that means like the modularity of this framework definitely helps with its robustness. And so I see that as a positive. And finally, we ask one more question, and that is code the necessary mechanism for question decomposition? And so we ask, can we do successive prompting and use a large language model for decomposing these questions in natural language instead? And the way that works in this diagram is you take the question like we did before, we give it to the large language model. It can either come up with a prediction or ask a follow-up question. The follow-up question is a visual question. It's answered by blip2, and the prediction is fed back in this loop. And then you might ask one more follow-up question and one more follow-up question. And then you might decide, the language model might decide to end and give a prediction. So we should look at some specific examples for that. On the left-hand side, we'll look at that example about the food the woman has been preparing, has it been fried? So first, the question might be, what's in the image? And that's just the first question we always ask. The answer for that question specifically is produced by blip2. So a person is preparing a salad on the counter. That's what's in the image. Then the decomposition network, which actually I forgot to mention, that's also codex. This large language model is actually codex, just like ViperGPT. And notice we just keep the blip2 module, just like ViperGPT. But this is the nearest neighbor architecture to the ViperGPT variant from our previous experiment, where we only kept blip2 and we removed the other modules. So then that codex will pose a follow-up question. So now that it knows that there's a salad on the counter, has the lettuce been fried? And so then you just ask the has the lettuce been fried question to blip2, and it'll say no. So then finally, the codex model, the large language model, will decide that it's ready to make a prediction, which is no. Similarly, we can look at the example on the very right-hand side. We talked about this earlier. And so the first question might be, what's in the image? The woman sitting on the couch playing a video game. Then what company produces the device in her hand? Nintendo. So the prediction will be Japan. Notice that there's a gap, there's a little jump between the previous answer Nintendo and the prediction Japan, which was unlike the first case, which was no in both cases. But it can do additional reasoning on top of the final answer. And so these are just a few examples. You might see that for more complex questions, it might decompose them into a few more steps as well. But it does pretty well on our task. So you can compare this to the equivalent variant of ViperGPT, the blip2 only variant. And so in that sense, these are computationally equal. In terms of the modules they're able to use. Both are able to use codex for decomposition, and both are able to use blip2 as the module they're calling. And so we do see some drops. I guess like code is more robust for certain cases, like VQA v2 and OK VQA comparing ViperGPT to ours. So ours is less performant, as well as this one. But there are some tasks where ours performs much better. For example, on GQA, that's like a +10 gain, +10, 12 gain. And OK VQA multiple choice setting. We saw that ViperGPT itself had outperformed blip2 significantly, and then our method continues to outperform that even more. And in science QA especially, that's a very large gap. So it is really benchmark dependent. It's dependent on the style of questions you're asking. But I think we said that no, the fact that these questions are decomposable in the first place is what's important. And then the means of how you're doing the decomposition, that varies. So if you use code, in some cases it can perform really well. If you decide to use natural language, in other cases that might perform well. So that's pretty much a summary of our work. And we have some ideas for future work in this area, because I don't think I think these methods are really inspirational, but I think they're just like one of the first steps in the future. It's a big step forward from 2016, but I think there's more work to be done. So, for example, you might have noticed in one of the earlier slides, we were decomposing the questions without the image at all. We were just decomposing the question about the muffins using the model with no image context. So it would be great if we can use the image context in the loop for decomposing questions. If you don't, that kind of assumes that the questions are decomposable. There's only one way to answer every. There's only one decomposition to answer every natural language question, which I think isn't the case, and the image context should help significantly. The reason we're probably not seeing that already is because I think it's pretty hard, at least last I tried, to decompose questions. So Codex is pretty much one of the only models that I found was really, really capable at doing this. None of the open source models, for example, I think I had tried OPT or Llama at the time. And I also tried the StarCoder, some of the earlier StarCoder models, which is the open source code generation model. You know, they might be able to autofill code or produce code, but they're not really able to decompose code into questions, especially using using like the API or the in-context examples. So you first have to get a model that does that, and you also have to get one that's a multimodal model. So maybe that's a step forward that somebody has to take. I'd also love to see a fair comparison between these models. I think a lot of the time these papers kept saying they are training free, but if you think about what work goes into building these architectures, it's true that while looping them together in this framework might be training free, actually it took a lot of training to train models like Codex or to train models like Blip2. So I think I'd like to see more fair comparisons between such architectures with equal compute or data pre-training, but that's a pretty big work. And I think we should. I'd like to see these systems being a little less complex because I think the more complex it is, maybe the more brittle it is to prompting, and maybe that makes it more robust to new tasks. But I think all three of these areas need to be improved as well. I'd also like to see more primitive and general modules because these modules that we saw were like specifically hand chosen for the vision language tasks we see in general. And so maybe we can look back to the 2016 work and say, maybe all we need is some kind of simple attention and decision-making modules. So I think this work has been really exciting so far, but I think there's a lot of work to be done. So I'd be really excited to see that. With that, that's the end of my talk. Thank you so much for having me. Happy to answer any questions.
Yeah, so we got a number of great questions, Apoorv. So what we can do with the questions, you guys can come off mute when we call your name, and you can ask the question directly to Apoorv, or if you want, I can read the questions, either or. So the first question that came in was from Vatsala. So Vatsala, do you want to come off mute to ask your question? Okay. Well, Vatsala's question was, from a much bigger model, how do you decompose to these modules specifically for only one class?
I'm not sure I understood. Could you repeat the question one more time?
Oh yeah, his question was, from a much bigger model, how do you decompose to the modules you were showing earlier, specifically if you only wanted to focus on only one class? So I think this question was pretty early in your session. So let's go back a little bit. Okay, a little bit more. and help me here, Benedict, to find the right slide.
Do you think this question was about the Viper GPT style work or about the neural module networks?
Yeah, it was probably about the general framework that the modular networks follow. Yeah, it was closer to the beginning of, yes. Yeah.
Okay.
So I think this is where the question came from. So if Vatsala could just provide a bit more context, that would be appreciated.
Yeah, Vatsalai, he might have actually dropped off the call. Are you still there?
Yes, I'm here.
Okay.
The question was resolved later on, but I just wanted to know if you could figure out these from foundation models too.
Okay, so figure out the decomposition part. Is that right?
Yes, yeah.
Yeah, I think so. Okay, then the question of what is a foundation model becomes a little trickier. But basically, what I was trying to say is that the decomposition, I only saw it successful in specific models like OpenAI, like GPT Codex, right? I couldn't find it. I couldn't get it to work in smaller open source models or even open source models trained on code. Hopefully that answers your question.
Yeah, thank you.
Okay, thanks.
Okay, we had a couple, we'll get to your question next, Benedict, but we had a couple of questions from Joseph. So Joseph, do you want to come off mute for your questions?
Hey there, folks. Joseph here. I have a face. Yeah, I had a couple of questions. I'm gonna skip my comment because, yeah, and okay, I'm a builder. I'm not, so I'm always like looking at the applied thing and looking for tips because, I mean, there's just so much out there. So basically, I was trying to squeeze the brain juice about just the modules, right? Because, okay, this is what happened to me last night. I found all the cool Google ones, and you can put them all together. Some of them are only 330 million parameters, and that can create such rich pipelines. It's all open source. And I was wondering if, you had like a top 20 favorite VQA module.
I mean, I can tell you that my favorite VQA module is probably blip2. Usually, yeah, I mean, I'm not sure I keep track of the.
Why do you hate
models.
SIG?
What is like SIGLib or?
SIGLib, yeah.
Oh, I don't hate it.
No, I'm just Josh. I'm trying to.
Oh, yeah, sure. Yeah, I mean, that one also comes to mind. I'm not sure I keep track of the specific, like, there's like an explosion of modules these days. I'm not like
right.
That
was my impression, but I'm not an expert. And I'm like, okay, let's look at what's going on. 150 since November. That's what it felt like.
I can keep up with that. I think blip2 is prominent. I think SIGLib, which you also mentioned, that one's pretty prominent too. I think you can just try to filter out which ones are the most performant, like those two, and focus on using those. Because at the end of the day, while your specific task might be well solved by a different module, maybe the gains are marginal, and maybe it's just not worth testing 150 modules in order to figure out which one is temporarily the best for your task. There will always be a better module tomorrow. It'll always be trained on more data. It might be bigger. It might have a better architecture. Yeah, that's just my take.
Well, thanks for that, because that's very insightful and based on experience. And I was about to embark on the opposite road. And I appreciate that advice a lot, because now I can just start to build instead of look.
That sounds good. And I mean, the best you might be able to do is you take one of these existing state-of-the-art off-the-shelf models, and then you tune it for your task. Now, in this talk, that's not what I'm like saying is a good thing, but like in practice, if you have one specific task that you want it to be good for, you should do that.
Okay, so we had a couple more questions, and we haven't forgotten about you, Benedict, but we had a couple more questions that just came into the Q&A from Vidushi. So Vidushi, do you want to come off mute to ask your questions?
Sure. Am I audible?
Yes, we can hear you.
Okay, perfect. Really great presentation, and it actually came in at a perfect time because this morning we were just talking with Microsoft about GPT-4V, and I was really looking forward to your presentation on the other end of things. So I believe that your solutions are more modular, and especially with the successive question part, which I really like, because that takes on the more agent-like approach to complex questions. So my first question was regarding the GQA. So I do know the benchmarking for GPT-4v, particularly where it performs poorly on GQA because it does have some indirect questions about people, and it just hesitates to answer those questions because it deems them unethical. So do you think that also was an impedance in GPT and also your task specifically?
Oh, could you repeat the last part of the question? I didn't understand the
Yeah,
the
in
question.
GQA, for example. So do you think even GPT or even your variant of it was a bit reluctant to perform on the GQA part because
Oh,
of some people-related queries?
not reluctant in the same way that you describe. I
Mhm.
think these open source, like there might be a difference in how those like products like GPT-4v are trained and these open source modules. These open source modules are typically just pre-trained on internet data or trained in some other way on internet data. And there's no concern with what they might output. If people are building things like GPT-4v and they need to make it an OpenAI product that many people will use, they might need to do like some safety considerations that make it more hesitant to answer questions. But like on one hand, you might see better performance out of those models. On another hand, you won't see such reluctance, as you're calling it, in these open source models.
Mhm. No, good insight. Yeah, I'm not really that familiar with the open source one because I was mostly focused in corporate just with the actual ones provided by OpenAI. The second question I have, and this is the last one, Benedict, so you can go after this. What, in your experience, was the average response time for the modular approaches compared to the end-to-end solutions that are already existing?
Okay, so when you say response time, you mean how long does it take to make
Yes.
one execution?
Mhm.
Oh,
The whole
okay.
execution, yeah.
So I think this is entirely bottlenecked on the large language, like all the models you're using. So I don't know, maybe you could say a few seconds, but like that's a few full seconds of compute. Remember that these modules I'm running, I'm also running all of them on a 40 gigabyte GPU, an Ampere GPU. And then the large language model is being run, it's an API call. You might have to actually, like in the successive prompting example I showed, I'm actually calling it multiple times. Well, first of all, to get each follow-up question, and then also to do other things like choosing tokens and things. But yeah, like I think it can vary, maybe between a few seconds to a minute, depending on how complex the architecture is. I think it varies.
Mm-hmm. Awesome. Thanks for the answers.
There is a code repo for this talk. I saw that question in the chat. It is at this QR code. At this QR code, and I'll send it in the chat. So a note here is that I chose to use Codex, OpenAI Codex, as the decomposition model in my work. And that is because I wanted to make a fair comparison with the previous work, ViperGPT. That model is now deprecated, as is like the specific API to call such models from OpenAI. So my code probably just doesn't work. I think my code is pretty clean, so it should be easy to use for these benchmarks and for creating your own method. You just have to fix those calls. Thanks, Joseph. That would be great. Were there other questions?
Benedict,
Yeah.
you had a couple.
I don't have so many questions because during the course of the session, a lot of the questions that came to mind ended up getting answered. So I just have one leftover question. So I observed that your version of your variant of Viper GPT seemed to outperform the original Viper GPT on a couple of tasks, and then on other tasks, it didn't actually make gains, it accrued losses. So I have a bit of a surface understanding of the work now. I have a better understanding of the work now that we have come to the end of this session. But I would like to hear from you, why do you think that is? Because essentially we are dealing with VQA, irrespective of the specific benchmark of interest. So obviously some benchmarks will probably have a couple of peculiarities to them. Maybe there will be difference in terms of complexity or stuff of that nature. But at the end of the day, we are still trying to solve the same exact task. So I'm curious as to why it will perform very well on the same task on a specific data set, and then on a different benchmark, it seems to flop. I'm just curious to hear what you think. Why do you think that might be so?
Yeah, sorry, I just want to clarify that I don't think in any of the results I actually presented, I didn't show that any of the variants of Viper GPT outperformed the original Viper GPT. I want to clarify that.
Okay.
Yeah, besides that, and so then if you look at my paper, then there was this table that I didn't show here in this paper. That's like about what if you do these kinds of, if you keep only blip2 or remove it. I don't completely remember, but I don't think there were many cases here either where the variant outperformed the original. Actually, there's only two benchmarks we have for the original, the GQA and OKVQA, and I don't think it outperformed it in those cases either. But maybe to answer the rest of your question, I think there are a lot of different skills required for these different tasks. For example, GQA is specifically I mentioned that they primarily used these two functions, simple query and best text match, to answer VQA questions. And I think that's pretty much because you can ask a single question about each example in GQA, and then you can do some kind of text matching, and that's just the structure of all the questions. So if you solve each of those components really well, you might solve the task.
Okay, thank you. Yeah, thank you.
Great.
Okay, well, we're at our hour now, and this was actually a fascinating session. So thank you so much, Apoorv, and we had some actually really great questions. So I saw a couple more questions came in near the end. So do you mind if individuals send you an email if they have follow-up questions, Apoorv, after the session?
Yeah, that's no problem at all for me.
Okay, sounds good, sounds good. Okay. Well, Benedict, did you want to go ahead and close it?
Yeah, thanks. Thanks a lot, Apoorv, for being here. This is very much appreciated. I was intending to read the paper in depth, but I just couldn't make the time. I had just had to mostly skim through the paper. But with just an hour of listening to you, I think I have a much better understanding of what the paper entails without actually having to go through all the work of reading it myself. In as much as I love reading research papers, it's always a good idea to cut corners when you can, eh? So yeah, thanks a lot. And I'm sure I speak for everyone on the call when I extend my gratitude. So thanks for being here. We really appreciate it. And thanks a lot to Amid for doing most of the groundwork. Yeah, he did most of the groundwork getting you here. So yeah, I would be remiss if I did not mention that. Yeah, thanks a lot. And thanks to everyone for being here too. Yeah.
Okay, thanks everyone.
Thanks so much for having me.
Yeah, thank you.
Okay.
Perhaps we can have another talk with you sometime if you are amenable to that.
Yes,
I
on
wouldn't
video
mind
next
that.
time. Video would be
Yeah.
great next time. Yes.
Okay, yeah, sure. So
Okay.
take care, everyone. If you have questions, you can also reach out to Apoorv. I think he's okay with everyone reaching out to him via email. Just be polite with your questions, and of course, yeah, that's all. That's all really. So thanks a lot for being here, and we'll see on our next session. Hopefully, sometime in the future, Apoorv will grace us with his presence once more, and we'll have more questions for him. Maybe on this particular paper, maybe on some other project he's working on. So we'll see. So take care and bye for now. Let's draw the curtains close. Yeah.
Okay, goodbye.
Yeah. Bye, everyone.
Thanks, everyone.
Yeah.